Well, good morning, everyone. Thank you so much for joining us today. My name is Victoria, and I'm a Senior Business Development Coordinator at 2H Offshore. We started this webinar series last year in April during COVID lockdown and held a live webinar every 2 weeks in 2020. Going forward, we'll be hosting the events monthly, so we hope you will continue to join us and find the information useful. Today, our webinar is entitled Challenges in HPHT Riser Technology, Design, Fabrication, Installation, and Integrity Management. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. So with that, I'm very happy to introduce our speaker today, Nuri Sagla. Nuri is a principal engineer at 2H with 12 years of engineering experience in design, analysis, and delivery of offshore riser systems. He specializes in design, equipment specification, and package management, fabrication and qualification testing of HPHT offshore welded riser systems. So with that, I'm going to pass things over to Nuri to get us started today.
All right. Thank you, Victoria, for the warm introduction. I am very happy and excited to be here to talk about on this topic, and I hope you will find all the information useful in the presentation. Okay, let's get started. Okay, today we will try to understand the key riser design issues and technology challenges in high pressure, high temperature conditions for the offshore riser systems. Our presentation today will mainly focus on the wettery riser systems. There are several challenges and technology limitations due to HPHT conditions, and these are design issues, fabrication challenges, installation limitations, and integrity management concerns. So we will go over these items one by one and try to understand the challenges and then conclude our presentation. So back in early 2000, late 2010, any design pressure around 10 KSI was considered as a high pressure system. And any design temperature close to 250 degree F was treated as a high temperatures. But today, the operators are looking to drill and develop deep water wells in the Gulf of Mexico. And these deep water wells, Gulf of Mexico, pressure ratings are sometimes become higher than 15 KSI. And the temperatures can become higher than 350 degree F. So when we look at the BSEE documentations, BSEE states that a pressure rating greater than 15 KSI is a high pressure system, and a temperature rating greater than 350 degree F can be considered as a high temperature system. So this is a new area for the offshore industry. And designing the system under these severe conditions, under these high pressure, high temperature conditions, leads to several challenges, which is stretching the conventional riser technology to their limits. And we need to understand the feasibility of wet-tree riser configuration in these severe environments and see the potential gaps between the qualified technology and then the HPHT requirements. As I stated, this is a new technology for the offshore industry. The first high temperature project was in the Gulf of Mexico in 2019. So it is a pretty new area for the industry. And that was the Shell's Appomattox platform based on the BSEE reports. So today, high pressure, high temperature conditions, and then for the riser configurations, the wet-tree riser configuration is selected. Why wet-tree riser configuration is selected for this presentation? Basically, Wettery riser configuration, wettery riser systems are the most common riser system in the Gulf of Mexico, and it's a very conventional technology. Compared to the dry-tree riser systems, it requires less capex, easy to design, easy to fabricate, and easy to install. It's just a single line pipe, can be a steel line pipe or a flexible line pipe, stretched from flow line all the way to the vessel. The shape, typical shape of the wettery riser configuration is the steel catenary riser configuration shown in the left figure in this presentation. Sometimes for the riser, steel catenary riser having some fatigue issues at the touchdown zone where the pipe meets the seabed. To mitigate that fatigue problem, sometimes designers prefer to put buoyancy modules to mitigate the fatigue problem at the touchdown zone. And then when you introduce the buoyancy modules along the riser takes a different shapes, and it's called a lazy wave riser. So that's a second most common wettery riser configuration you can see in the Gulf of Mexico. And the good thing for these riser configurations, they can be attached to any vessels. They are good with the semi-submersibles, spars, TLPs, and FPSOs. So we will focus on these riser systems for the HPHT design conditions. Okay, the first thing we need to understand is the internal fluid conditions in the HPHT conditions. If you look at the different design guidelines, such as API TR17, TR8 states that even if your fluid doesn't contain any H2S, you need to consider your system as a sour system, considering the possibility that H2S content may increase over the life of the project. If you look at the BSEE documentation, there is an NTL 2009 G3, and it says that a pressure rating higher than 15 KSI, any H2S content higher than 3.3 ppm will put you in the sour system. And there is a nice plot here showing base from the NTL. That is the red line, which is showing the H2S partial pressure of 0.05 psi. And then y-axis is the pressure, design pressure of your system, and x-axis is the H2S concentration. And this red line is showing that any H2S partial pressure above 0.05 psi is a sour. Any pressure lower than 0.05 psi is a non-sour environment. So what this figure is telling us, for example, let's take a 3000 psi pressure. For the 3000 psi pressure, to be able to make you the sour, your H2S concentration can be up to 20 ppm. But as you increase your pressure, your H2S concentration will go down. For example, for the 15 KSI, if your H2S concentration is around 3.3 ppm, you are in the sour region. So there are two disadvantages here because of the high pressure. One is you need to detect very small H2S concentration to understand whether you are in the sour region or non-sour region. So it is difficult to detect that low-level H2S concentration. And that is the reason why API TR17 TRA is saying that even if you don't see any H2S concentration, you need to design your system for sour conditions. And second disadvantage here is any slight increase in the H2S concentration over the life of the well will again put you in the sour region. So that's the first challenge for the high pressure systems. And that is the second requirement per the NACE. Again, there is a plot here coming from the NACE document. X-axis is the H2S concentration. Y-axis is the pH of your internal fluid. And as I stated before, a H2S partial pressure of 0.05 is a boundary line. Any pressure, any H2S pressure less than 0.05 is a non-sour region, which is region 0. But any pressure higher than 0.05 psi H2S pressure, it will put you in sour regions. Region 1, region 2, region 3. Region 1 is the mild sour region, and region 3 is the severe sour region. The disadvantage here, in addition to the H2S, if the project is planning to acidize the well later in the life to improve the efficiency of the wells, the acidizing wells will come back to the production flow line as a spent acid and will decrease your pH. And if you decrease your pH, which is the y-axis in this NACE plot, suddenly you will be in the region 3, which is the severe sour region. So pressure plus the spent acid, possible spent acid, will put you in the severe sour regions. And if you look at the NACE requirements, NACE says that if you're in the region 3, your hardness, maximum hardness in your riser can be 250 HV10. So it is another challenge to achieve the 250 hardness value in the riser system. HPHT environments, as I stated, it is a new environment, it needs new design conditions. So operators basically cannot use the existing equipments because the design condition exceeds the existing equipment's capability. So operators need to redesign or develop new equipments to accommodate these severe HPHT conditions. And then in order to put these equipments in the service, they need to carry out advanced planning and then do the design verification and validation per the BSEE requirements. Again, BSEE states that if you are in the HPHT environment, which is pressure higher than 15 KSI and temperature higher than 350 degree F, you need to verify, qualify, and validate your concept. And then BSEE needs to approve your concept before you go to the project phase. And BSEE requires another requirement. BSEE has another requirement for the HPHT environment. After you do your concept validation, the concept has to be verified by an independent third party, which is called as I3P. So I would like to highlight that BSEE has two requirements. One of them, BSEE says it for the HPHT conditions. You need to validate your concept prior to project phase. And validation process is the I3P process. And when you go to the project phase, there's another validation process. But that validation process in the project phase is called as a CVA. So that's another requirement for the HPHT conditions this BSEE dictates. All right, so we are talking about the high pressure and high temperature system. One of the challenges of the HPHT steel pipe wet-ray riser system is the steel pipe wall thickness. There are several design codes that you can design your system and then come up with the wall thickness sizing of your steel pipe. One of them is the 30 CFR 250. There is a burst equation that you can use and then come up with your wall thickness. But that equation is very conservative and it will yield to very heavy wall thicknesses. So BSEE per NTL 2009 G28, it says that we don't have to use 30 CFR 250 conservative equation. Instead, we can use API RP 1111. And then if you look at the API RP 1111 wall thickness equations, that document is talking about the temperature derating factor, derating of the material strength due to high temperature. And that temperature derating can be different based on different codes. There are some derating factors per the DNV codes, some design factors per the API and ASME will give you a different temperature derating factors. And designers should be careful to apply this temperature rating, especially if you are in the higher temperature rating. And if you don't know the project specific data, pipe data, it might be challenging for you to come up with the temperature rating factor for the wall thickness sizing. So that's one of the issues a designer should be careful with the high temperature conditions. So we are talking about the pipe wall thickness. Of course, as you increase your pressure and increase your temperature, the pipe wall thickness go up. And the plot showing on here is showing the pipe wall thicknesses of X65 pipe for the 10-inch OD riser pipe. A pressure 15 ksi, 17.5 ksi, and 20 ksi is considered. And the temperature is changing from 250 degree F to 350 degree F. If we look at the latest design efforts done by operators, maximum wall thickness qualified up to date for the HPHT SAR environments is 1.9 inch. So what we are saying that our existing technology limit for the steel pipe wall thicknesses for the wet riser system is 1.9 inch. So if we set that as an existing technology limit, and if we look at this graph, we can see that for the 10-inch pipe, that's the most common OD for the steel catenary riser systems. 15 ksi pressure system can stay below the existing technology limit. But for the higher pressure, like 17.5 ksi or 20 ksi systems, the pipe wall thicknesses will exceed the existing technology limit, which is 1.9 inch, and it will become more challenging to produce and manufacture that pipe. As you increase the pipe wall thicknesses, it becomes more difficult to manufacture the pipe. One of the challenges is the pipe manufacturer need to optimize the macro alloy composition to achieve the required mechanical properties, to achieve the required CTOD values, to achieve the required yield strength values. The pipe manufacturer need to optimize the macro alloy composition. So recipe of the pipe is important. And as I stated before, since we are in the HPHT condition, which is in the SAR condition, and per the NACE, we have to be careful with the hardness. So the hardness value is important, and meeting the hardness value for the SAR service application is another challenge for the thick wall pipes. Of course, thick wall pipe means that heavy pipe. It is difficult to inspect, and quality control of these thick pipe walls is difficult in the pipe mills. And another challenge is, if you are designing your system per API, for example, you need to do the hydrostatic and burst pressures. And then for the thick wall, conducting hydrostatic or burst pressures requires test pressures greater than 20 ksi, sometimes 25 ksi. And an equipment to be supplied that kind of high pressure is difficult to get in the pipe mill. So that's another challenge for the pipe manufacturing process. Okay. Next design challenge is the crack face pressure. If you introduce a high internal pressure in the system, that internal pressure will affect the crack and then try to open the crack more in the design. Usually, effect of crack pressure is ignored in the conventional fracture mechanics approach. That should be okay if you are in the low pressure region, like a 12 ksi, 7 ksi. That shouldn't change the design. But if we are talking about a 15 ksi or 20 ksi systems, that pressure becomes important and needs to be included in the fracture mechanics design. In the conventional veterinary riser application, loading in the axial direction is typically governs the design. And an axial loading in the riser opens up the flow in the welt in the circumferential direction. However, for the HPHT conditions, we have a high pressure, means that we have a hoop stress. And that hoop stress is opening up the cracks in the axial direction instead of circumferential directions. And if you have a localized pitting due to corrosion in the axial directions, it is important to consider these effects in your fracture mechanics design, including the crack face pressure. And there is an example here that I would like to share with you to demonstrate the effect of crack face pressure. An example here is an 8-inch OD pipe. A wall thickness is 1.9 inch and a design pressure is 20 KSI. And this plot is clearly showing that this blue line is the fracture limits of the SCR pipe without including the crack face pressure. And the red line is the fracture limits of the SCR pipe, including the crack face pressure. And let's take an example of the 80% wall thicknesses. If your flow depth is around 80% of the wall thickness, your fracture flow length is around 120 millimeter if you don't include the crack face pressure. But if you include the crack face pressure in your design, then suddenly your fracture limits will go down. For the same flow length, let's say flow length of 120 millimeter, only 42% of the pipe wall thickness will be sufficient to stop the rupture. So that's another things to designer needs to be careful for the high pressure systems. Okay, next one is the fabrication and inspection. After the pipe is manufactured, the pipe joints needs to be welded. And then welding is challenging, especially to meet the hardness requirement. During welding, you introduce additional heat on the thick wall pipe, and that will make your pipe more harder, which means that your hardness will go up. And it is challenging to meet the hardness requirements dictated by the NACE. Second is since the pipe wall thickness is very thick, very high, it requires multiple weld passes, as is shown in this picture here on the left below. And one other thing is that consistent temperature levels throughout the pipe wall thickness is difficult to achieve. In the conventional welding technology, the pipe is preheated before welding using conventional torch flame technology. Basically, you using torch to heat your pipe from the OD. And then one thing is you have to be consistent temperature from OD to ID. Making the temperature levels consistent from OD to ID may be easier for a thinner wall pipes. But if we are talking about 1.9 inch wall thickness or 2 inch wall thickness pipe, maintaining the consistent temperature levels from OD to ID is difficult to achieve. And the fabricator needs to be careful to make sure that preheat levels at OD and ID should be around the same temperature. So there's another challenge and making the fabrication more difficult. Of course, we are talking about the sour region, and we need to have a high quality welding in the root region where the pipe is directly exposed to the potentially sour environments. High quality welding means difficult to fabricate and then more fabrication times. In addition, we are talking about the thick wall pipe, high quality welding. Welding equipment needs to be developed or modified, and that will bring another challenges to the system. In addition, if you are changing your weld equipment or if you are redesigning your weld equipment, you need to train your welders again. That's another challenge. And of course, for this thick wall pipe, after welding, the inspections and AUT inspection is challenging, especially to detect fatigue sensitive flow sizes in the root region. So definitely fabrication and inspection is difficult. Okay, coming to the insulation. As expected, as we increase the pipe wall thicknesses, the weight of the pipe will go up. Means that the weight of the riser will go up. And that's an issue for the insulation. And as we increase the pipe wall thickness and as we go to the deeper waters, there are limited number of insulation vessels to install this kind of thick wall SCRs. And then this plot is showing that two configurations, basically relay and then J-lay, based on the published installation vessel documents, the real lay tension limit is considered as 2200 kips, and J lay tension limit is considered as 4400 kips. And if you look at the 8-inch and 10-inch pipes from 15 KSI to 20 KSI design conditions, for the 8-inch pipe, even for the deeper water wells, rail lay and then J lay is a feasible installation technology for the high pressure levels. But if you are talking about 10-inch pipe or even 12-inch pipe, and as you move to the deep water wells, feasibility of rail lay becomes more difficult. Of course, J lay can be done, but relay is a preferred installation method due to the cost constraints. So that's another challenge, especially for the ultra deep water wells if you are designing heavy wall SCRs. Next one is the hang-off systems. Typically, there are 3 configurations that you attach your riser to the vessel. The first one is a flexible joint, or you can use steel taper stretch joint or a titanium taper stretch joint. If you look at the current flexible joint technology, we can see that approximately 13 KSI design pressures and a temperature of 250 degree F is the design has been used so far in the Gulf of Mexico. So if you are talking about 20 KSI and 350 degree F, it is very challenging to use the flexible joint in the as a hang-off system. Second option is using this steel taper stretch joint, but again, that's going to be a very thick taper stretch joint, and due to very high tension because of the thick wall pipe, it requires very long steel taper stretch joint, which is going to be difficult to fabricate and difficult to install. Plus, it will add more weights into the hull. Another option is to use a titanium taper stretch joint. That's one of the most feasible options for the HPHT configuration. Can be used. One limitation is the titanium can be susceptible to the acid, and then the production, if you are using the titanium stretch joint, you cannot acidize your wells directly through the production flow lines. So that's one of the limitations for the titanium stretch joint. Next one is the corrosion inhibitor. Basically, corrosion inhibitors are used to mitigate carbon steel corrosion due to the internal fluid. And then as you increase your temperature, it becomes more difficult to use corrosion inhibitors. Typically, the effectiveness of corrosion inhibitor reduces as you increase your temperature. And there is a nice paper is clearly showing here is this plot here. For the 180 degree F temperature, you have the same corrosion inhibitor in different concentration, 20 ppm and 100 ppm. And as you see that my corrosion protection is almost 100%. But if we increase the temperature to 350 degree F, then suddenly my protection goes down. So that's one of the disadvantage. And second one is you have to for the temperature, it may, for high temperature, it may affect your corrosion inhibitor integrity. So you may lose the chemicals integrity in the corrosion inhibitor, and that will that may block the injection system. And if you are trying to use a corrosion inhibitor in the high temperature conditions, you need to use higher chemical dosages compared to the lower temperature conditions. And the second, this plot is showing here, is showing that you need to select a right chemical intermediates to come up with a good composition for the corrosion inhibitor. Even if you get a good right intermediates, the composition is important. And this plot is showing here, you have a D, E, F, the same chemicals for the configuration one, and DEF same composition for the composition 2. The same chemical elements but different compositions will give you a different protection. So you have to be careful with that as well. So the chemicals, right chemicals, and in the right compositions are very crucial for the corrosion inhibitors in the high temperature region. Flow assurance is an important element in the design and operation of flow lines and risers. And flow assurance means that is a uniform flow rates along the production rates and steady state temperature conditions in the production lines. And if we are talking about a high temperature, like a temperature 350 degree F or 400 degree F, traditional thermal insulation materials may not be applicable to high pressure, high temperature systems. So the operators needs to come up with an advanced polymer designs to meet the flow assurance requirements. And that's another challenge. You may find a good polymer to meet the high temperature conditions, but you also need to look at for the availability and the cost perspectives to understand the implications and impact of the system. So that's another challenge for the high pressure, high temperature systems. So in conclusion, production from high pressure, high temperature wells results in challenging problems, and as well as components putting into the service is a new technology. When you put the new technology in the service in the high pressure, high temperature systems, you need to have a very advanced plan. You need to develop a very advanced concept. You need to validate and qualify that concept. And that concept has to be verified by independent third party. And again, the new concept has to be approved by the BSEE prior to going into the project phase. And there are several critical areas considering the wet-tree riser configuration in the HPHT environments. And in this presentation, we covered engineering, design, and qualification testing challenges, thick pipe wall manufacturing, thick pipe wall welding and inspection, increasing weight, installation challenges, hang-off system challenges, the corrosion inhibitors, effectiveness of corrosion inhibitors in the high temperature regions, and then thermal insulation due to high temperature. Those are the key challenging areas for the HPHT systems for the wet-tree riser configurations. And that's what I have for today. I hope you can find the information useful. And if you have any questions, please feel free to ask and we can discuss right now.
Thank you so much, Nori. That was awesome. We've already had some questions, so I can start with those. And if anyone has any more, we'll probably have time for a few more. So you can go ahead and send them to me in the question box, and we will take them one by one. So the first question is, what is the most challenging part of the wet-tree riser systems in HPHT conditions?
All right, it's a good question. Actually, we listed the challenges here. We listed the pipe fabrication, pipe manufacturing, welding, inspection, and installation, thermal insulation, and corrosion inhibitors. Those are the key items. But when we look at that one, as I stated before, let me go that slide, back to that slide again, is I'm sorry, where is it? Okay, this NACE requirement. Basically, NACE is saying that if you are in the severe SAR region, region 3, your hardness requirement shall be less than 250, your hardness less than 250. And to weld the pipe, to weld the thick pipe wall, and then try to stay below 250 is challenge. And maybe the most challenging part of this system. Maybe that is the most challenging part because it is difficult to weld and achieve this target hardness value, and it requires a good quality welding, very good quality welding, and very good quality welders, and it will impact your speed for the fabrication and installation. So this is maybe the most challenging area if we are talking about the welded wet-3 riser systems.
Okay, thank you. Next question. Is there any restriction of CRA application on the ID size to protect from corrosion?
Well, there are some project qualification has been done for the cladded wet-3 riser systems, typically at the hang-off region, but for the high pressure, high temperature systems, there is no fully qualified technology with the cladded systems, and it is difficult for the cladded system. Two things: you have already a thick wall pipe, 1.9 inch or 2-inch pipe. In addition to that, you have a clad at the ID of the pipe, which will bring additional complications for the AUT inspections. That will becomes more challenging. As I stated, what we see in the current technology, we see that non-clad welded pipes typically are preferred and qualified today, but unfortunately there is not much qualification efforts for the cladded pipes. Yes.
Okay, great. Next question. Besides welded pipe systems, is there any other technology to be used for HPHT?
Yeah, I mean there are several, as I stated, there are several different riser configurations. Today we are focusing on the wet-3 riser configurations. Dry-3 riser configuration, like the top tension risers, also can be used in the HPHT conditions. Of course, there are some other challenges for the dry-3 riser configurations. Or for the wet-3 riser configuration, you can use a flexible pipe instead of a steel pipe. But the challenge for the flexible pipe, if you look at the current technology, 6-inch ID flexible pipe is qualified for the 20 KSI. But if you require higher flow areas like 8-inch and 10-inch flow areas, and if you are talking about 20 KSI, there is not actually fully qualified flexible riser technology up to today. And then one other disadvantage of the flexible pipe is if you are talking about the ultra deep water wells, and flexible pipes are prone to collapse pressure. So there's another challenge for the flexible pipes. There are some options, but they come with their own challenges. Yes.
Okay, thank you. Next question, if I can get to them. Okay, we can reduce the pipe wall thickness by using higher grade pipes. So are there any additional challenges using the higher grade pipes?
Okay, so let's go to that slide. Okay, so there's a good question actually. In this plot, I am showing the pipe wall thicknesses for the X65 pipe, which is 65 KSI material. So if we use X70 pipe, we can of course reduce the pipe wall thicknesses slightly, or X80 pipe, you can reduce the pipe wall thicknesses. But again, the welding an issue, hardness an issue. If you want to use X70 pipe, the welding becomes even more difficult. And then meeting the hardness requirement, 250, even more difficult. As you increase the yield strength of the pipe, you are making your pipe more harder. And then your hardness will go up. And then meeting the NACE requirements for the SAR service region even becomes more difficult. So yes, you can reduce the wall thicknesses by using higher grade pipes, but can you weld that higher grade pipe? It is very difficult. So typically, if you look at the operators, they still prefer X65 pipes in the wet-3 riser systems.
Okay, thank you. Got a few more. What materials have been considered for the HPHT systems for cladding and uncladding pipes? And do you follow the DNV OS F101 for this subject, including fatigue analysis? So I guess two parts.
Okay, fatigue analysis. Okay, the first one is the cladding and non-cladding material. For the cladding material, again, as I stated, for the HPHT conditions, we don't see much qualification efforts. There are some qualification efforts has been done previously, but not fully completed. For the non-clad pipe material, again, that's the typical API 5L seamless pipes are being used currently. Again, it's the same conventional materials, so materials doesn't change. But again, as I said, the microalloy composition, typically the recipe of the pipe is changing. So that's the change in terms of the material. Regarding the code, well, it is a for the fatigue design, it is a project specific. Some operators prefer to use DNV codes. Some other operators try to use their own qualified SN fatigue curve. So it is DNV OS can be used, but it is dependent on the project and operator's decision, actually.
Okay, thank you. Next question. Would thermoplastic composite pipes be an option for the HPHT challenge?
Thermoplastic composite pipe. Okay, composite pipe. Well, that's a good question. You know, it is not covered here. Still, I mean, thermoplastic pipes typically is not currently is not considered the veterinary riser applications because it's a new area. You have to go all this full qualification process again to prove that the new material is applicable for the HPHT conditions. And typically operators, what we see up to today, operators still try to use the conventional technology and tweak the technology or modify the technology and try to use it again. So what we see here is they prefer to use a steel material, which is a conventional material in the system. That's what we see here. Of course, there's another topic can be looked at it, but that requires a brand new development and then a qualification process.
Okay, thanks, Nori. We've got time for one more. Can we use smaller OD pipes and thinner wall thicknesses to utilize conventional technology for HPHT design?
Okay, good question. Yeah, that is related to this plot again. Again, this is like this wall thickness is given for 10-inch pipe. If you increase your OD like a 12 inch, your the wall thicknesses will even go up higher than 2 inches, higher than 2.2 inches. It becomes even more difficult. Reducing the OD to 8 inch and 6 inch will reduce our wall thicknesses, and we may go down to less than 1.9 inch. But let's take an example of 6-inch pipe. If you design a 6-inch pipe under 20 KSI systems, your ID could be less than 4 inch. And then it will bring another question. Is it going to be sufficient for the flow line requirements? Are we going to get a sufficient flow area due to the smaller ID? So we need to look at the flow line requirements as well and try to understand what is the limitations from that side. So it can be used, it will reduce the wall thicknesses for sure, but you need to look at the flow area.
Okay, great. And I am just going to squeeze in one more question. So there's been some studies in Brazil trying to use a sandwich solution, which is 2 steel pipes with a concrete core. Could this be another direction to compensate both structural and thermal challenges?
Well, I'm not familiar with that concept. I mean, We are mainly concentrating on the wettery riser system in the Gulf of Mexico. That's a new technology. Again, HPHT conditions require a new technology, brand new technologies. So this could be a new technology, but again, has it been used in the Gulf of Mexico? Has it been ever qualified even for 10 KSI pressure? Has it been used in the before? So those are the things that needs to be answered, and operators typically do not intend to use brand new technology and try to put it in the very severe environments. Again, what I said, it can be used, of course. I'm not familiar with that concept, but the questions here, is it can be qualified, and does operators willing to, are operators willing to use that system? Those questions are actually can be to be answered.
Okay, great. Well, thank you so much, Nuri, for all the information on the topic. That's all the time that we have for today. But as we mentioned earlier, if we didn't get to your question, or if you'd like to continue this discussion, you can contact Nuri directly using the details provided here. And thank you to our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series happening at the end of each month. Check out the 2H website and LinkedIn for more details and to sign up. Again, please look out for the recording of this webinar in your email in the next 24 hours, and we hope you all enjoy the rest of your day. Thank you.